everyone, this is the continuation video of lesson 4.1. So last time we talked about example 1, example 2, so now we move on to example 3 and example number 4. Example number 3. Marlo exerts a force of 280 newtons on a rope angled at 50 degrees to the horizontal in order to pull a 130 kilogram sled a distance of 40 meters. How much work does he do? So let's try to take note that he's exerting a force. However, it is angled to the horizontal at 50 degrees and the mass is 130 kilogram and with a distance of 40 meters. So how much work does he do? So this is the same thing as, since he is exerting 280 newton of force, it's the same thing as with that 280 newton of force, how much work does he do with that particular applied force. But we need to remember though that it is angled off at 50 degrees. So if we're gonna start with a diagram, so if we're gonna draw this particular situation, we have, say, our box or the sled. So if this is my sled and then I exert a force, but it is angled off with the horizontal. So if this is my F, this is 280 newtons, okay, and it is said that this particular force is angled off at 50 degrees with the horizontal line is this side here, that's the horizontal, and it travels at a distance of 40 meters. So this is it moves with a d of 40 meters. So it moves at a certain distance. So you can also draw that displacement is in that direction. Okay, so now if we're gonna just rewrite the given, again, F is the applied force is 280 newtons, angle theta is 50 degrees, and D is 40.0 meters. So to answer the question, work is given by F cosine theta D. So we're given the force of 280 newtons multiplied by the cosine of 50 degrees and displacement of 40 meters. Again, as mentioned, the work done on the object is just the component of the force that is parallel to your displacement. So that is given by that F cos 50 degrees. So that is that particular force here. So in the same or parallel with the displacement. The displacement is to the right, so just the force parallel to that. So if we're gonna do the computation, that would be 280 multiplied by cosine of 50 degrees times 40. So the work done is given by 7,199 joules, or in two significant digits, that would be 7.2 times 10 to the power of 3 joules. So again, if you have noticed, I'm not using 280 times 40, but just the component of the force that is parallel to the displacement. Now let's move on to example number 4. So I'm just gonna take note of the given by highlighting them. An 8-kilogram wagon is rolling along a sidewalk. A force of 60 newtons is applied in the opposite direction to bring it to a stop in 2 seconds. So bring it to a stop in 2 seconds. So stop means that V there is equal to 0. So the question is, how much work is done? How much work is done? So let's say, for example, again, I'm gonna start it with a diagram. So if the wagon, this is my wagon here. Okay, it's rolling along the, so let's say, for example, the velocity is in that direction. Okay, so the force is applied in the opposite direction. So there's a force in this direction here, so that is your F. Which is 60 or 60 newtons. Okay, but it is moving, well, in this case, in this orientation, it should be moving to the right, because the direction of the applied force is the opposite to that. So the displacement would be given by this, but that's a question mark. It moves. What you're given though is that it will stop in 2 seconds. So again, the displacement is going to the right. This is your displacement. Okay, so the displacement is to the right, but the applied force is to the left. So if we're gonna write the given quantities, so I've given the force of 60 newtons, and I've just given the time of 2.0 seconds. And what else am I given? I'm given the mass of 8.0 kilograms. The final velocity is 0. And what else? Well, what is your theta in this case? So your theta would be, if you can see here, force is to the left. This is my F. So if you're gonna look at the angle between them, this is 180 degrees. So this is 180 degrees. So now for my solution, I'm gonna start with the formula of F cos theta D. So if you can see here, F is given. That's good. theta is also given, but d is a question mark, so you don't know d. So therefore we cannot use directly the work equation given by that. So what we're gonna do is we need to solve first d. So solve first d. So solve for d. So how do we solve for d in this case? Well, what we have is the time, which is equal to 2.0 seconds, and I'm given also the final velocity of 0. However, acceleration is not given. Okay, so if you can remember our kinematic equations, those kinematic equations that we had, we can use those, the displacement equations, if at least 3 variables are given. So in this case, it's quite obvious that we only have 2, the final velocity and the time. However, if we can solve for the acceleration, I think that will give us 3. So based on the things that we have here, do you think we can solve for the acceleration? Well, remember that kinematics and dynamics are related to each other. If you can remember, second Newton's law tells us that the net force acting on the object is equivalent to its mass times its acceleration. So if you go back here to our drawing, the only force acting on the wagon here in the x direction, or in the x component, is given by F. Okay, so again, I'm just looking after the forces along x, because anyway the movement is along x. So the force in the x direction, or in the x axis, is just given by F. So ma, or a is equal to F over m. F is given as 60 Newton, 16 newtons, divided by the mass of 8 kilograms. So in that particular case, you can get the acceleration of, so the acceleration would be 60 divided by 8, which gives you 7.5. meters per second square to the left. It's to the left because the net force, if you can see in your drawing, it is also to the left. Okay, it's to the left. So now that is my A. So A, or you can say that A is equal to negative 7.5. Again, conventionally we use to the right as positive and to the left as negative. So we know that A is equivalent to that. Now we can somehow revisit our kinematics equations. So in order for us to solve for the displacement D, so which of the kinematic equation do you think you can use in order for you to solve for D? So just gonna extend this one here. So you now have again A as an additional, it's negative 7.5 meters per second squared. So which of the kinematic equations do I need to solve for D? So you have the time, you have the final velocity, and the acceleration, and then I'm finding for D. So my question mark is D. So that would be, well, you have the equations, final velocity is equal to VI plus AT. Well, in this particular equation, you can get the initial velocity of the object, because this is 0, VI plus negative 7.5 times 2, or the initial velocity should be equal to 15, so positive 15 meters per second. So from there, the initial velocity is that, I can use the equation VIT plus AT squared over 2. So the displacement is VI, so this is 15 times 2 plus negative 7.5, 2 squared all over 2. So the displacement is 30 minus 15. So displacement is equal to 15 meters, positive or just 15 meters to the right. So 15 meters to the right. So now I can use that value there, so this answer here, to solve for the work. So work there. So work is equal to 60 cosine of 180 degrees multiplied by 15. The convention there is positive, so this is 60, and then the angle is 180. So cosine of 180 is negative 1. So you can check that one in your, so work done is 60 times negative 1 times 15. So that gives you 900 joules. But the convention is negative, or work is in 2 sig figs, that's negative 9.0 times 10 to the power of 2 joules. So in this example, if you can see, the force is anti-parallel to the direction of the displacement, as expected, you get a negative work. So actually the force is doing negative work on the object. Again, that happens if the force and the displacement are in the opposite direction. So that's it for this video, and in the next video we will be talking about the force distance or the force displacement graphs. Okay, so see you next time.